I was trying to bring about MuBot. Well, how's everyone doing? Kayla, good to see you. I was going to have MuBot appear. He sometimes just doesn't want to appear. He's going to do it? Oh my God.
Now I am here. Why was I not here anymore?
He just, I don't understand. Good to see you here, Nolan. Good to see you here. Kayla, let's throw out 100 points. I have no idea what's going on. Why is MuBot? I know, right? I was trying to bring him out on the main screen.
There I am. Brian was trying to do this, but he failed.
Okay, let's get serious here, everybody. Let's get serious. It is time for some serious music. Let's go grab the activity. And good to see you, Nolan and Kayla. Nolan and Kayla both here. Good to see you. Give out some 100 points. We're going to start up some activity here. I'm going to go grab the activity. Simple regression. Oh, went to wrong class. Simple regression. Part 1. Crazy idea. We're going to actually do some regression. It's the name of the class. So we got regression part 1 coming up right here. So let's take a look at regression part 1. Ridiculous idea. Let's do regression. Name of the class. And we will start covering it. I'm going to go to quizzes. We'll be posting it here in just a little bit. The quiz, is it posted? Activity. Let's get it posted right here. There's a problem with the questions not connecting. Oh my gosh, it's connected. It's actually working. The quiz is published. It's good to go. Quiz is no longer broken. Quiz is out till the 4th, which is Friday. And let's go download the data. Let's show it right here and let's start talking about that quiz. Awesome. Ella, great to see you. Yep. Do you see the activity 5 now, Ella? I was doing some changes to it, getting it fixed up. Should be good to go. Ella, do you see it? Let's go check it out. Who sees activity 5 right here? Activity 5 instructions. Who sees activity 5 right here? Do we see activity 5? Do we have the data set? Do we have the practice file? Do we have all of this right here? How are we doing, everybody? Are we seeing the Xbox data? Are we seeing all of this right here? Oh, you're not in our session. Oh, you're not in our section, right? Nolan sees it. Kayla or Ella, are you on Discord? Or do you want me to email you this? Are you on the Discord, Ella? If you're on the Discord, I can directly send you this. Let me see if you're on here, Ella. If you can message me on the Discord or send me a quick email, I'll send it to you. Your teacher should be posting it. Let me know, Ella, and we'll make sure you have it all so you can follow along. And so, yes, I'm on the Discord. Message me real quick on the Discord. Just say hi or something, and I'll send you those files real quick. So just click my name at the top right there and say hi, and I'll just send you those files, and you can follow along. And your teacher should be posting it up. There you are, Ella. Oh, yeah, were you? I think you're on. Oh, just a lot of awesome. Great work on all that work there, Ella. And so that one has an extra. This has a -1 on it. I don't think that's going to. Okay, so this file right here, Ella, has a -1 on it. All right, here's the activity. Sending you the activity as I speak. There's the activity. And let me get the activity 5 without the -1 on it. I don't think theirs will. So I'm searching. Oh, I did activity 6. Activity 5, no. Okay, it's being crazy. Activity 5. Okay, here we go. Okay. Here it is. Okay. Here's the file, Ella, and there it is. Awesome, Ella. So you should have it now. Ella, sound good? We should have it right here. 100 points. Ella, thank you so much, and good practice right there. So we have right here the practice file, the RMD, and we have the DAT file. And so let's go take a look at the activity right here and see what we got. Okay, so let me know if you have questions at any point. We have the assignment, we have the files. It's just a few practice problems we're going to do on this to make sure we understand the basics of simple linear regression. You're welcome, Ella. So what is the biggest condition for doing linear regression? Kind of one of the most important things we should know about linear regression is we're about to put a what through data. Just think here about linear regression. which kind of goes to the idea of correlation. We were talking about correlation today in 201, or not 201, but office hours. The idea of correlation is a what relationship with variables, hence the idea of linear regression is built off of this. Like this does not have good linear quality to it. So I keep saying the word, yep, 2 quantitative variables right there. Kayla, great work. 2 quantitative variables, we can analyze the linear relationship. And there are things where it doesn't apply, where we have relationships that are not linear. So we see correlations of 0. Now, you might say, well, what does the simple word mean of it? Because we don't understand what we're talking about. Regression just means we're doing like regressing a line through it. We're doing an equation. We're regressing one variable over another. But the idea of simple means one variable. So, well, we should put that in the quotes, right? Or the parentheses. Simple means one variable. Linear goes to the form of it. And then regression is like the mathematics. Does that make sense? So what do we get if we put this together? We got one variable form mathematics. It doesn't really make sense, but simple means we're using one x, so we should say one x variable. And linear means we have a form to it that we're putting a line through it. And regression means it's mathematics where one variable is regressed over another. So let's look at this right here. Download the activity 5 Xbox auction .dat to your BAS 3.0 folder. Make sure to put it there and run the library reg class to load up all the functions we'll be using. And now we have to do the read.csv. Now do make sure that this file is in your files folder. Sometimes it might have in a -1 after it, like this. I think I can load it that way because I have that version of it on my computer. And I also have this version. Who's with me right here that this is loaded? And you need to make sure you download the file. And when you download this file right here, you might see maybe it has like additional things after it, but look how it downloaded and make sure it has that name. Now you can always go in and rename the file, but who's with me that you've now loaded in this Xbox data right here to your global environment? Everyone good on that? That's like key number 1 step is get your data inside of R. This is just a CSV file on your computer. Make sure it's saved. You can load it in. You just need to make sure you have it in the right folder. And then you do the read.csv, download both of those, check the file name to make sure it either has like this right here, the -1, or it's just this right here. And I'm not trying to type this. I'm just going to copy paste. Yep, done. 100 points, kill it. Perfect work right there. Like this step right here, if you don't get this step, you don't have the data, then we can't do the analysis. I'm so sorry, but every time we use the dot file, I won't open it. So you don't double click it. Great answers right there, Nolan, in question. If you double click it, it probably will open inside of Jump, but run the following code, Nolan, right here. This code I put in the chat right there, run that code, and it's going to store that to your global environment. So if you download a file, which it might do the same for me, I wonder if I'm going to try double clicking it or clicking it. Actually, it's saying it won't open. And it says try an app on this PC. So I could get it to open inside of Jump, or maybe, or Atom or something. Did I download like a browser thing, or what is Atom? I forget. I've put so many different things on this computer. Now it's opening inside of like a thing right here. I had to put the -1 on yours. Yep. If you have to put the -1, so you might have to put the -1 to make sure it opens. It just needs to find that file. Sometimes it will download with the -1. Sometimes it won't. I know it says like here, Xbox auction. So it shouldn't do it. It's in my 320. I ran that and it says error. Did you put the -1 after it? Because people, like Kayla said right there, sometimes you have to put that -1 because it might have downloaded that way. Like make sure to look at how your file looks, and it might have your -1 on it. So if yours has a -1, then do the -1. If yours has the -1, use a -1 right there. Might even try to like, let me see if I can fix some of these issues right here. So that way people come back here. Let's go look. Might have happened when we copied the Canvas course. So get the data. Number 1 thing is get the data. Why is it? I click up there at the top. Watch it make it like a .2 or something. Okay, it should not have any file extensions after it now. It could be even crazier now for all I know. But it shouldn't have any. It shouldn't have any. It shows that. Got it. Great job, Nolan there, 100 points. Let me know whenever you have problems. I just looked at my computer, copied the name from exactly. Look at your computer, find out what it is in your folder down here. So whatever you see in the files folder down here, like when you go to the files, look at what it looks like, and then use that name that it says, whatever name it says under your files. So click your files, look at the name, whatever the name says, good to go. The dataset contains 149 Xbox auctions right here with from the Xbox 360, you know, old school gaming nowadays. The variable of interest is price. When we say variable of interest, that is what we're wanting to understand. That is the what variable. Price is now the what variable right here. Price is the what variable. So if I say price is the variable of interest, I'm trying to tell you that is the what variable. So if I say price is the variable of interest, that is the what variable. When I say variable of interest, the one I want to understand, the question of why, that is the what variable. So if it's the variable interest, it's the why. James, great job right there. Good practice. It's the why. No, that's the exact answer. The variable of interest is sometimes called the why variable, the response variable. You'll just hear these names a lot of times, and it's good we practice knowing what someone says when they say the variable of interest. That's the one we want to analyze. So we want to understand the y variable, and then we're going to use these x variables to explain it. Like maybe the bid rate on the Xbox explains its price. Maybe the opening bid of an Xbox explains what price it's sold for. Make a scatter plot to determine the relationship between price and bids. A linear regression model is appropriate when the overall trajectory is straight enough. And so let's look at this right here. We are going to do the following, and here is how to make a linear model. Let's put some notes. And let's put a timestamp here, making our first linear model. Preparation, okay. Preparation and timestamp right here, making our linear model. I feel like there's some that can, yeah, exactly. Some can be X or Y. Some can be X or Y. Here's our format. You ready? Let's break this down. Y tilde X comma data equals like this. So when you look at this, why do you think we store into object M? Which you can call it different things, but I usually call it object M. What do you think M is short for? We're making a linear what? Like a linear what? And why do we usually call this M? Oh, no. Yeah, well, yeah, email me. I might give the points back. Email me or Discord me, Kayla. I might give you the point backs. Well, it's going to, yeah, that's a good answer right there. This will make it easier storing it to M. And why would we call it M? Why don't I just call this object, why don't I just call it Brian, which you could for all intents and purposes call it Brian. You were right, Ella, right there. We're going to call it M for model. So M is just short for model, and some people do like M.1 or M.2. Whatever model they're making, they might just say like this model or M.linear or something like that. Some people use like notation afterwards, but we usually just do M because it's a one-letter abbreviation for model, and we're storing the linear model into the object M. So this will create the object M. So we need to know our Y variable of interest. Our Y variable of interest is going to be the price of an Xbox from the bids of an Xbox explained by. We want to understand price. We want to understand bids. Why will my code not run? My code will not run when I do this, and why? It says bids not found, but bids is in there. Bids is in that data frame. So very quick common error right here, but we need to make sure if we see something like this, we know immediately what to do and immediately what to check. Why will it not run? I said price explained by bids. This is Y tilde X, no capital B. Ella, following along perfectly. We need to make sure we capitalize the exact way, and now the code has evaluated. Great job, James, right there. So we now have stored the model. We can do so much now. The world is wide open to us. One thing you might do is you might plot it. And I was answering someone earlier that was making the plot of this. They were plotting it the following way, which is all right to do. It's not my favorite way to plot things. But you could plot the model doing the following. And I'll show you why I wouldn't do this in a second. Col equals red. There we go. So this is a plot of the model. This is one way to do the code right here. What I have right here, and I'll explain the code, is plot uses the same syntax of Y tilde X comma data equals, and then I'm appending onto it an added line. So you have to append on an additional line of code that says use an AB line. I call it AB line a lot of times, but it's called AB line, which is like, like 2 points connecting a line, like point A, point B, creating AB line. And then M is the line we're creating, which is the model. And then the color is going to be red. You can do more with this, which is kind of neat. You can do things like line width and set the line width to something like 4. And now you can get like a thicker red line or whatever you'd like. But here's the thing. You remember how I said this object M is something we can work with? We just covered this in 201. What are we trying to do with our model? Think of a word. We are trying to what our model right here with this plot. We are trying to what our model with this plot right now. Like the whole point of this plot is to what our model. The whole point of this model, this thing right here, is to what it. The whole point of this plot is to what the relationship with the variables. Like, oh, we should do this with it. We should, what should we do with it? And this is why life gets really easy with some neat codes that we are going to show here in a moment. Kind of simplified, communicate ideas right through a visualization. Good job right there, Ella. We're going to visualize it. We're going to like create a scatter plot that visualizes our model. So how about visualize? Oh, I didn't run reg class. Library reg class, because it's the first time I'm using one of the functions, and visualize model M. There's the model. It's got extra information, which we will not be covering this week because this is in simple linear regression part 2, the confidence and prediction intervals. We are interested in this red line, which I also made as a red line here. It zooms in a little bit so we don't see the extreme outliers over here. So there are a little bit of outliers, a little bit of heteroscedasticity. For the most part, is this linear? For the most part, is this model linear? Yes or no? Which is our big thing right here. Is it linear enough? For the most part, this is the same model, just visualized with 2 different visuals, zoomed in a little bit on this second one right here. For the most part, is it linear? As in, does this red line right here go through the middle of the points? For the most part. For the most part, yes. And I would say the big issue, great job, Ella, right there. I'd say it's mostly linear. I actually have to be off the screen so you can constantly look at it. I'd say it's mostly linear, but there is a small problem right here. For the most part, yeah. It's mostly linear. If I am to say where a problem is at on this, it's not going to be with the linearity of it. The problem is going to be over here with the outliers. For the most part, the stream of points is well defined by the red line, or the red line goes through the center of the points. These are more of an outliers issue. So I would say there is a little bit of outliers that we have problems with. And we have lots of ways to analyze this to come to more concrete conclusions if those points have undue influence. To give you a very quick glimpse into the future, I said those points have undue influence. Tell me 3 letters if I want to check the influence of stuff to see if points have undue influence. This is probably 2 weeks from now. But if you were to say, I want to see if these points have undue influence, what 3 letters might you start typing right here to see if points have undue influence on your model? What 3 letters would you type to start maybe looking for a code that tells you if they have undue influence? Let's see if anyone takes a good guess right here to see like, you might, there's 2 combinations. I'm seeing which one you might type. But if you want to investigate undue influence, what 3 letters might you start typing? Because once you type 3 letters, autocomplete kicks in. And then you get to be like, oh, I'll just use this. Makes life really easy. We'll see what chat says. I'm on top chat still. Live chat. So when we start typing 3 letters, it will give us suggestions on code. So outliers, which is a big thing to know, outliers can do anything to our regression, right? So we don't like these points over here because outliers are going to drastically impact the value of our regression, right? So the idea of influence is outliers influence our model. Does that make sense, Kayla? Like it seems straight. Like the relationship in the data seems straight enough. Like the line goes through the middle of the data, but a different question, which is not the straight enough condition, is the no outliers condition, is do those outliers have too big of an impact on our model? Does that make sense to what I'm asking Kayla right there? Like, do those outliers have undue influence? So if I were to try to figure this out with code, because there is a code to look at this, what 3 letters do you think I would write to start looking at the question of, do these points have undue influence? So I'm trying to see, is there too much influence from the points? And so if you hear a word I keep using, that might be part of the code right there to look into this question. And I just want to show you the ease of which we can do a lot of codes right now. The code is, notice how that's in reg class, influence plot. Do you have any idea, Kayla, what I should put in here? And this is a good thing to make people feel good about the future. INF exactly. And then what do you think goes inside of the function? What do you think goes inside of the function? And this is a really good thing to know about the future, because the big thing is not writing all the code, but knowing what the code does and knowing how to write it. But this is an easy thing. What do you think I put inside the influence plot function? To look at the influence of the model, I should probably put what inside of it as the argument. Don't worry, it's not complicated. That's it. How many points have undue influence? Be careful. This is an advanced question, but don't be tricked by it. I'll explain the answer, but Kayla, I'm going to throw 500 points, 200 points for a guess. And then we're going to go back to the main point of this lecture's video, but I just want to show some ease of which. How many points? Kayla, 500 points. You did it. 1 point. And this is the row number of that point. That is the row number of that point. Row 8 has undue influence on our model. And I bet if we were to look at it, it's probably like an Xbox that had like a weird combination of prices and bids. That is the point that has undue influence. Oh no, the answer is 1. The row number of the point is row 8. So we could actually go and look at that right now by just going here. And row 8 has undue influence. Row 8 is an Xbox that sold for $306 and had 42 bids. So that point has undue influence from the model. I think it's because it has a lot of bids. It has a very high amount of bids and a pretty high price, but it has undue influence on the model. That's the row with undue influence. So pretty interesting right there. But once again, I do want to point to the coding gets easier. Like influence plot is just influence plot M. So once again, we wanted to analyze for this question, is it mostly linear? And that's a huge condition for linear regression. And the answer is via the plots, whichever plot we look at, the line does look to go mostly through the data. There does seem to be an outlier issue with this model. We've already fit the simple linear regression right here. And so since we've already created it, we're good to go on that. Code creating the model. I'd use the ab line. Oh, is this the same thing? What? Well, cool. We already did that. As you can see, the slope of the model is not very steep. So here we go into some really tough questions. However, it does not fit the data better than the naive model. Ooh, so I had a really good question. Someone started off the stream by asking, how do we create the naive model? Let's put a segment in this video here on the naive model. So if you are born into the world naive, the naive model, if you are born into the world naive, what do you know? You're like tabula rasa. If you're born into the world naive, what do you know? If you're naive to the world, what do you know if you are naive? Could I, yes, send it to me on Discord, I'll take a look. Or drop it here in the chat, Ella, and then you can delete it afterwards. Send it to me on Discord or drop it in the chat. Either which one, I'll take a look, I'll run it. Keeping the same layer on AB line. Could I send, yeah, send it and we'll, all right, here we go. Ella's got it. Can you send me, oh, because you have to append the code. Here, Ella, I'll drop the code for you. Here, I'm gonna drop this for you and then make sure it's on one line. Let me do this. And great work, Ella. There it is right there, Ella. So try running that right there. And see, it has to be like appended on the same line because it like runs it. And Kayla's right. If we are naive, we know nothing. So how many, so think about this. The X or the naive model has how many variables in it? You know nothing. You're Jon Snow. Jon Snow is the naive model. So how many variables, how many X variables does the naive model have in it? How many X variables? So if we go here to Y tilde X, data equals, then we go Xbox. What's up, Adam? So good to see your 100 points, Adam, showing up. If we have, you're right, Kayla. That's the answer. Now, it's really weird. It's all on the same like line right here, Ella. It's all on the like it's all like this. It has to have that appending to it. You might have to send me a screenshot of your send me a screenshot of it, and I'll see maybe how it's being run. But it all has to be on the same like line with an appending of the code to do the AB line. Not the biggest fan of doing the AB line because the visualized model does it for you. So teachers should accept visualizing model. Now this is really confusing. This is a little confusing. Okay, just go with me on this. To get no X's in the model, we actually put in 1. That's, oh my gosh, what did I do? Oh, capitalized letter. So this right here is the naive model. The naive model, Exactly. Oh, yep. It like appends on it, like makes the plot and then like goes to it and appends that line to it. So it's like an appending. It has to be appended, which is kind of weird. But you have to run it. You could highlight all the code and run it, or I think that'll work, or I just append the code to make it run. Good answer, Zella. Because it's like an additive code. It has to have the plot and then it has to have the thing added. So if you look right here, a naive model, and take these notes, would only have the what. A naive model would only have the what. Ah, now the dot is different. So this is the naive model. And the dot is different. The dot doesn't mean only the intercept. The dot is what we call the full model. So let's put M naive right here. And let's put M full. So if you take a look at the full model, how many variables are in the full model, which we're definitely not going to do today. Think of the full model. The full model has how many variables in it? So this is y tilde dot versus y tilde 1. Y tilde 1 gets you the naive model, no x's. The full model, which is y tilde dot, is what x's? The full model, which we call like the full model, or what do people call it? They also call it the saturated model sometimes. The saturated model, the complete model has what x's in your model. And take a look at the data here. Take a look at the model. The full, the saturated, the complete model has how many x's in it? So this is y tilde dot. So if you put a dot, you get how many x's? How many x's are currently over there? Of these x's up here, how many? So look right there at those. And this is the y tilde dot combination. Is there just one x? I see bids. I see duration. I see open bid. How many of these are over there? So all of them, exactly, all x's. So think about what a full model means. Does that make sense? A full model has all, and great job, Ella and Kaylin. Don't worry, we're just here to practice. It's all of them. So if you want to take all the x variables, you can do y tilde dot rather than writing them all out. Or if you just want no x's, you can say the y tilde 1. But these are important codes right here to remember for the naive model or for the full model. Those are just shorthands for it. Y tilde 1 is the naive model. Y tilde dot is the full model, which includes all the x variables. So with this right here, we're not going to write out the full model. So we're just going to right here and do a little block comment to this. So let's say, bye, it's gone now. We're going to talk about the naive model here for a moment. Now, I want you to think about this. If you were to walk outside and you were to guess the height of UT students, you walk up to a random person, you know nothing about them. You are Jon Snow and you know nothing about them. What would you guess for the height of that person? Walk up to a random person at UT and just guess their height. What would you guess? Random person. You know nothing. You never look at me. You just say, hi, random person. There's someone near me. I can't, I'm not touching you. There's movement near me. Okay, you're this tall. Random person. 5'6". Pretty good guess right there. What are you going to guess for the next random person? You guess 5'6". I'll take that right there. What are you going to guess for the next random person? Next person walks up. What are you going to guess? I can't see you. I can't see anything. I just hear rustling. I mean, I don't know any. I can't see anything. I just, there's noise. That's all I know. It could be a dog for all I know. But a random person, I think. I'm going to guess what? Huh? Well, maybe. And we'll go with Kayla's guess right here. For the next random person, what would you guess, Kayla? For the next random person, what would you guess? 5'6" again. You're exactly right. And the next person and the next person. What do you notice this kind of looks like if you think about this? And Nolan, your guess is great too. I like both your guesses. Because Kayla, your guesses are going to look like this. And why would you guess 5'6"? 5'6" probably sounds like the what for a lot of people. 5'6" might be the what of your y variable. And this is an important concept. The average. Because you're like, well, I guess the average, females are maybe 5'3"-ish, men are maybe 5'9", 5'10", that's about 5'6". So I guess, on average, people are 5'6", right? That's what the naive model is. Think about this. All you would need to know for this is where it hits the what. If you were to look at this model, you would just need to know one value to create it. And what value would you need to know to draw this line? The line has a slope of 0. There is no slope to this line. You only need to know the what for this line to draw it, the intercept, and take a look. Right here, that's what this model gives you. It gives you the y-intercept. So you know what this value is? Just get ready for it. Get ready to be shocked. That value right there is the mean of y. So the naive model predicts everything to be the what? It has no x's. So the naive has no x's. Does that make sense? The naive model has no x variables. So the naive model predicts everything to be the what of y. Just repeat it again. This is what we need to know conceptually. The naive model has no x's. All it knows is the y variable. So it just says, well, I guess everything's the this. It just makes a flat line. That's the what of y. That's every prediction from the naive model is this. It's just like, well, you're this, you're this, you're this, because I have no other x, I have no x variables. I'm just going to predict the what of y. So what does it predict? The naive model for every observation would predict the what of y. What does the naive model predict for every single observation? The naive model has no x's. It uses no x variables. All its predictions are done from the y variable. And it would predict the same thing. It's just a flat line and predicts the average value of y, so then it's not using any x's. If you notice on my drawing right here, the drawing has no x down here. It's just like there's no x to care about. It's just everything. We could put any sort of x values down here, but it's just going to be a flat line, as flat line as I can make, where it predicts the mean of y at all points. So good stuff right there. So here's where we need to know what the SSE of the regression model is. The sums of the squared error. These are big concepts. So let's talk about sums of squared error. Some people say, I hate coding. Well, welcome to theory. Sums of squared error. Okay. So this goes back to 201, because when you think about what is an error in a regression model is also known as a what? An error in a regression model, I'll give you a hint, is the actual minus the predicted, and the predicted is y hat, and this distance right here is known as a what? A residual. Oh, a great answer right there. That is a residual. That is E for residual. So residual equals actual. Oops, I did actual in green. Actual minus, and then the predicted. So once again, I like to say residual wrap. Residual equals actual minus predicted. That is what a residual is. Residual equals actual minus predicted. So why am I talking about the residuals for the sums of squared error? Well, E right here, maybe they call it E for error, but E is residual. Wrap right there, we know residual equals actual minus predicted. Take a look at this. When we talk about the sum of the squared error, what do you think we could do to a residual even visually to get the squared error? We could turn this residual into, if I could accurately do it, we could turn it into a square. I don't like that it kind of hit that one on the dot, because that's just coincidence. Sure, there, it won't hit it now. We could turn this into a square, and that's that residual squared. This is this residual squared, as best I can draw. That's that one squared. Here's this one squared. Why would we square the residuals? Who knows conceptually why we would square these things? Hint, some are positive, some are negative. Why would we square the residuals? Conceptually, why do we square them? Like, why not just find the sum of the residuals? Who knows why we wouldn't just find the sum of the residuals? Because I just squared every residual. So why not just sum the residuals? Like here, I'll go do that right now. Let me go to my model, and it's easy to get the residuals. We just go to residuals. Ah, James, exact answer, yes. Because if we take the residuals from our model, there's all the residuals, and let's just take the sum of them. Well, some are positive and some are negative, and the sum, if you don't know what that is basically 0. That's basically 0. I did too many zeros on it. But that's basically 0 right there. If we sum them all up, we get 0 because some are positive, some are negative. So there's some decimal change that doesn't work. But if you just sum them up, some are below the line, some are above the line. So we square them so they're all positive. And James said it perfectly right there. If we square them, it's all positive. And then we want to find out how much error there is, so we sum them. So think about this conceptually. The reason we find the sum of the squared error, the error is how much we miss by. We squared them so they're all positive, and then the sum is like how much error there is. So all we're trying to figure out is how much does our model miss by? And that's what we are seeing here visually with the sum or the squared errors. You can see there's pretty big misses over here, and it doesn't matter if they're positive or negative now, they're all squared, so they're all positive values. That's what a sum of squared error is. So we could go right here and get our sums of squared error for this model by doing squaring of the residuals. I wouldn't suggest doing it this way. That should be the sums of squared error. Now let me check it with a better way to check it. It wants the sum of the squared error of our regression model, which should be able to be found this way. And there it is right there. I would suggest using the ANOVA, and I do have a naive model right now. This is the sum of the squared error of the naive model. Let me store our original model as model M, and let's talk about the original model, which it might be asking for. But does that make sense that the naive model has this much error? Who understands me that the naive model has this much error in the residuals? Does that make sense? Like, that's how much error the naive model has. Like, the naive model misses those points by that much when we take the errors and we square them and we sum them up. That is how much error there is with the naive model. Now, we want our model to do what? Awesome. So that's bad. That's error. That's how much we miss by. We miss by that amount squared. So that's a squared error right there. But what do we want? We want to what that error? And there's a key word. Who knows what we would like to do to this error? We would like to what the error? So that's how much error there is to start. And then we want to what that error. So frankly, we did a starter question like question 0. Let's put this right here. What is the naive model's sum of squared error? That's what we just answered. We want to reduce it. So the naive model had this much error. And let's put that right here. So the naive model can be seen via the ANOVA. And we'll do the naive right here. That's the error of the naive. And then our model, which we called M now. Make sure you have your model saved with M. You can view it's the model with one variable. If you look at this, there's our model with one variable. And so now let's do the ANOVA of it and understand what we see. What's bad? What sounds bad right here? Residuals or the X variable? So what sounds bad right here? Residuals or the X variable? What sounds like misses? Like if I talk about misses, like when we miss certain things in the model, is that the residuals or the X variables? Like what sounds like is going to be part of the misses of our models? So what's going to be the misses where we miss the variable, where we don't predict things accurately? Those would be what's. So we have to know what this output's telling us right here. Talking about that one. I'm showing the old one, which doesn't have any X's and still has misses. So where are the misses? They're found in the what's of the model. The misses in our model are found in the which? The X variable or the residuals? The residuals. The residuals are how much you miss by. The naive model even has residuals, but it doesn't have X variables. Our model right here has residuals of this. So guess what? This is the what. What was M again? I deleted it by accident. Yeah, let me get that. I'll drop it in the chat for you. What? There you go. What is the sums of squared error for our current model? Now be careful with the one X variable model. The sums of squared error is what? For the one X variable model, the sums of the squared error is what? For the one X variable model, take a look on the screen. For the one X variable model, the sum of the squared error is what? Like how much we did not explain. The one X variable model has a sums of squared error of what? Double check. I think grocery's at 6 p.m. today. The 1x variable model has a sums of squared error. Yep. The 1x variable model has a sums of squared error of what? So look at the 1x variable model. Here's the 1x variable model, and it has the sums of squared error of what? So you have to know where to look in the output. What is the sums of the squared error of the 1x variable model? Ella, perfect answer. You're right. Yep. Excellent work. That's the answer right there. That is the sums of the squared error of the 1x variable model. Now, you know what's really interesting? Can anybody solve the following equation, who can solve this in their head? Can anyone solve this right here? Here, let me try to figure it out. I bet that's 61,879. 61,879. Because this right here is the what in the sums of squared error. So what I just did right there is the what in the sums of squared error. Take a look at this number, which is the naive model, the naive's error, what we started with, then our model, and then I just found the what between these two right here. So I just found the what between those two. A few words you could use. The difference, right? And you could call that the what in the sums of squared error, which is a key word to know. It's like we are trying to not have error in our model. We just found the difference or the reduction, how much we reduced the error by. And that is how much our x variable explains. Does that make sense what's going on right there with the code? Like, do those values make sense where they're coming from? Like, this reduction from the naive to our current model is this reduction is the difference between what the naive was at in error and what we're at now. Like, there's less error in our model. The x variable is doing some explaining. Who's following me on this right here? That the x variable has accounted for that much variation because it's reduced the error in the model from what it was at to the error that it has now. So this is the reduction in the sums of squared error accounted for by the x variable. And if you hear that, I just said this is what the x variable is accounting for. And I want to show you, now that we know the reduction and we know the naive. So here's the ANOVA on the M, and we can look at reduction of this right here. Let me ask you a big question, which I don't think is on here. Calculate R squared. R squared is the percent of variation in Y accounted for or explained by X. The variation in Y would come from the what? Like, don't think of any X's. The variation in Y would be from the what? So the variation in Y, like which of these numbers right here is the variation in Y? Like, where are you measuring how much error there is in the Y from the Y variable itself? Where would the variation in Y come from? Like, inherent variation in Y with no X's. So where would that come from? The inherent variation in Y with no X's, naive model. Where is that going to come from? Like, we'd be thinking the amount of variation in Y is this. Where would that come from? Well, the residuals is how much we don't explain. The residuals is what we don't explain. So, but true, Caleb, the residuals from the what is true. This is the correct answer. If you say the residuals from the what, that is true. If you say the residuals from the what, that is very true. Caleb, 100 points. You're on the right track. The residuals from the what, because you have to remember, it's the inherent variation in Y itself. So if we looked at the residuals of this, that is the correct answer, which is how much error there is in the Y variable or how much variation there is of the naive model. Great job, Ella and Caleb right there working together. The residuals of the naive model. So the naive model has this much variation. We explained this much variation. Does that make sense? Like, we explained this much of this. Does that make sense? That was the reduction. We have explained this much of the total. Does that make sense? So watch this. Do you see that value right there? That is your R squared. We just calculated R squared by knowing the amount of error in the model and then saying what amount of variation, at least from the naive model, did we reduce in our model. So our model is trying to explain the variation in the Y variable, which is why R squared is the percent of variation in Y explained by the X variables. So there's variation in Y, and that's from the naive model. And then we try to explain the variation with our X by reducing the error in the variable. A lot of big concepts right here. A lot of big concepts. If you got through that, you got through some of the biggest parts I'm trying to explain to you right now, which is basically this whole week's lecture. So you're kind of getting one of those mini lectures right now, understanding all this. Now, here's what's really cool. We got so many fun codes right here with the all possible regressions, which show us possible regressions. So possible regressions right here is going to do what? Possible regressions are going to show us random whats. Let me explain the possible regression output right here. Possible regressions are showing us what's of our data. So possible regressions are showing us what's of our data. Random what's. Random what's of our data. Possible regressions are showing us random what's. Random possibilities are permutations. If you were to randomly permutate the variables, most of your lines would be very what? Like all of these are random chance lines, and here's our line. Most of the lines would be very what? All like kind of sort of possible lines, like possible lines created by random chance, given that X and Y have no relationship. So random permutations where we just take the points and like shake them up in a box, and we're just like, okay, make a line with this now. And someone's like, but you just randomized it. And you're like, well, what would you get? Most of the lines look very what over there? Most of the lines look very what? And think they look kind of like the naive model, right? They look very, very what? A lot of the lines created by random chance relationships would often be very what? They'd often, just like our naive model over here, they'd look by random chance to be very what? Think they don't have an XY relationship. It's unlikely to get an XY relationship by random chance. So a lot of relationships that linear or like flat, right? So when X and Y don't have a relationship, it looks very flat. Like there's no real relationship between X and Y. It's just like a flat line, which doesn't have changes in X associated with changes in Y. So when you look at this right here, a flat line, would it do much better than the naive model? Lines that are very flat are like the naive model. So their reduction would be very what? So finish the sentence. Lines that are very flat would have a very what reduction in the error. Lines that are very flat would have a very what reduction. So these lines that are very flat would have a very what reduction in the error with the residuals. They would reduce the error very what? Have a very what reduction. Flat lines, which are not that great, not that statistically significant, would have a very what reduction in the error for our model. What would a flat line do? Would it reduce it a lot or have a very high reduction? Very small reduction. You might say, well, is 10,000 small? Remember, there's a lot of error. We've got like, what was it, like 500,000 error? So our line reduces it by this much, and then the random chance ones only reduce it by this much. So when you think about it, there's a very minimum or small reduction in the amount of error. So yeah, it's like, it really doesn't do that well. These random chance models are not doing so well. Our model does a lot better, and it's unlikely to see the reduction we got by random chance, meaning we have a statistically significant relationship between the bids an Xbox got and the price it was at. Great job, James and Ella right there, and Kayla, great work. So with this, we got some interpretations coming up right here. Regression predicting price from a completely unrelated variable always gives some reduction in the SSE to the naive model. The question is whether the reduction is large enough, all this good stuff right here, and p-values. Yes, yes, yes. So now we get to the interpretations. This is a big section of this video, and let's mark it. Here we go. Interpretation of regression output. This is probably going to be the most watched section because this is where test questions come into play. Of regression output. Okay, here's what I want you to do. Grab a sheet of paper. Grab a sheet of paper. With this right here, you get a cheat sheet on the test. It's great to memorize these. It's great. I highly suggest memorizing them. But you get a cheat sheet. It's going to break my heart when on the test I see interpretations that are way out in left field. It should be, even if they're bad, even if you make some mistakes, there should be some parts that you have right. But I'm going to give you hints right here, and I'm going to tell you how to do these and to get A's on the test. So let's bring up our output, and let's get ready to put it on our cheat sheet. And we have all these values to interpret. I'm going to add one more here, A, B, C, D, E, F, G. I'm learning the alphabet still. Let's say here, SE of slope, because that is on the assignment. Should cover all the assignment questions. Oh, it is right there. Standard slopes right there. SE of slope. Cool. So let's get ready to start interpreting these, and let's do it. We're going to put in a chunk. I'm going to say regression summary. How could I possibly get a summary of my regression model stored into M? Who knows how I could summarize my regression model? So think what I'm going to type right here, try to figure it out. Like we have a model stored into M, and I want a summary of this model. Ooh, there's the intercept, there's the slope. But how could I summarize this regression model right here? How could I summarize it? Summary of M. That's all we're going to do. Go here to summary. Great job right there, Ella. There we go. So let's get ready to read through this and go through it step by step. Okay, I'm going to start here at the very top. This right here is the way you wrote your formula. You'll see right here it says formula because the first argument is a formula. So it's just saying formula equals. We didn't actually have to specify that because it knows the first argument is a formula, so it assumes we put a formula there. We did y, variable price, x, variable bids, and this comes from the data set, Xbox, the data frame, rather, Xbox that we have right here. That's what that all means. The residuals are how much we miss by, and I'd like you to point out, or I'd like you to see right now, there's a very what residual. There's a very what residual. And we saw this all the way back. There's a very what residual. It's that one right there. There's a very what residual. You should think, what is this communicating to me right here? It's giving you the quartiles or quantiles of the residuals. And what do you see right here? Like, where is that over here? So these are all the residuals quantiles, which are going to be like the lowest residual, the highest residual, the median residual, which hopefully you have some sort of symmetry here. That is a very large residual. That is that point right there, which is far away. And once again, I said, I think we do have some outliers. And I think that was the point. Maybe that's not the one that has undue influence. It's a long story why that one doesn't. But do I get it right here? That's that point, I think. Doesn't have enough leverage. Topic for another day. So there is a very large extreme residual right here, which is a bit of an outlier. So why might you look at residuals plots? Or why might you look at the residuals? Residuals would help you locate what? Residuals, which this did perfectly. This could give me some indication if there's what's, because notice there's not a symmetry. Negative 100 is probably about one of these. Those are the ones that are about negative 100 below the line. And then residuals right here might help me locate what's. I just used the residual output right here to locate what. What was the point of looking at the residual quantiles right there? Outliers, Ella. Perfect. So you think, why would I look at this? Maybe I can identify if there's some outlier issues. And yeah, there is. That is 350 or so above the line. And that looks to be that synth. So it's that distance right there. I just want to show it visually so everybody knows I've got it up. That 347 represents that point right here has a distance of 347 above the line. It's 347 units above the line. So just so we know what that's communicating. Okay, so now we get to some interpretations. Interpret the intercept. First off, let me ask you, what is the intercept? So round it to 1 decimal or just round it totally. But what is the intercept? What do we estimate the intercept to be? So that's a good way of saying it. What do we estimate the intercept to be? Anyone just tell me the intercept. This is not how we interpret it. But what do we estimate the intercept to be? What do we estimate it to be? You'd say, Brian, I estimate the intercept to be this. What do you estimate it to be? 98. Right here, that's what we estimate it to be. So the intercept is estimated to be 98. But let's interpret it now. That is, what is the intercept? Not how to interpret it. So when x is at 0, we expect y to be at b0 on average. That is how we interpret it. Try writing now just one sentence, but write one sentence. Remember, we are predicting the price of an Xbox from the bids. Try it right now for 100 points. Write one sentence. When x is at 0, we expect y to be at b0 on average, which might be illogical. So I think this one actually is illogical, and I'll explain why, but try to interpret this. So you have to think, what is my x variable? So your x is going to be down here. When x is at 0, then we expect y to be at this. When the bids are at 0, we expect the price to be not 0, close, Ella. And then B0 is the notation for what B0 represents, or I'll highlight in the output. The notation we use for the intercept. I get it on screen. You're super close. I think you'll see it. Yeah, exactly. This is B0, and that is B1. because B0 is when X is at 0 and B1 is things that differ by 1 unit. When bids is at 0, we expect the price to be at 98 on average. Now, here's where it might be illogical. If these are things that sold on eBay, so let me say this. When the bids of an Xbox are at 0 bids, we expect the selling price to be 98.0410 on average. This is illogical because it would need at least 1 bid to have a selling price. It's a little bit tricky right there, but I'm pretty sure if it gets 0 bids, it doesn't sell. And we could maybe go look at the data set right here. We might not have any. I clicked the wrong button. But I think it needs a bid to sell. And you see the lowest we have is 2. So I think if it doesn't get a bid, it doesn't sell. So when the bids of an Xbox is at 0 bids, we expect the selling price to be this on average. This is logical because it would need at least 1 bid to sell. So it can't have a selling price if no one bid on it. A little bit tougher, but always ask yourself if it makes sense. Just think of what you're communicating to someone like bids. Xboxes that generally get 0 bids sell for this amount, but the model is illogical because we don't have Xboxes that low. Now, here's the thing I'd like to point out too. We're actually doing a what of this model. So if you look at this really closely, the model doesn't go to 0 bids. This is a good concept, which I think we cover this week and should be mentioned. We are actually whatting this model, stat1 concept, the intercept, because the data does not go that far. Here's a hint. We're not inside the X bounds of it. The data, we're making predictions here, and the data only goes to here. So the intercept is actually a what of the model. So it's outside the bounds of the model. It's extrapolation. And that's why we might say it's illogical. Watch out for intercepts that extrapolate beyond the model, because then you don't have data there. So it doesn't even make sense, because apparently I think you would need at least 1 bid to sell. So Ella, great practice right there in memory from Stats 101. That's an extrapolation of the model, because we don't, even though it's really close, it's just like you can't do that. You can't go that low because you would need a bid to sell. Yeah, great work. Ella, another 100 points. Great work. Good memory right there. Extrapolation. So the intercept is illogical via extrapolation. We'd probably just say to someone like, it doesn't make sense. Like, don't worry, the intercept is illogical. Like, I might just say that if we're talking to someone, be like, well, yeah, around 2 bids, we would expect this much. Well, let's do the slope right here. Now, this is where people lose points on the test. Okay, this is where points are lost. Do not say for each 1 unit, do not say this. Do not say for each 1 unit. I grade these for my students. Oh, great job, Ella, right there. Do not say. I know I touched that in 201, but don't say it here. I wish I could get 201 on board with this. And I'll explain to you why. For each 1 unit sounds like cause and effect. What we want to say is this. Here we go. 2 blanks that differ in X by 1 unit are expected to differ in Y by B1 units, where the blank with the higher, I knew I was doing that, with the blank with the higher X is expected to have the blank or Y. This is the one you need to write down. This is where the mistakes happen. It sounds like it's going to be super complicated, but let me just tell you. 2 Xboxes that differ in their amount of bids by 1 bid are expected to differ in their price by $1.76, where the Xbox that gets more bids is expected to have a higher price. Does that make sense when I say it to you that way? Like, I know that seems super complicated, but if I say, 2 Xboxes that differ in their amount of bids by 1 bid, the Xbox that has more bids is generally expected to have a higher price, about $1.76. 2 Xboxes that differ in their bids by 1 bid are expected, or 2 Xboxes that have 1 difference of bid are expected to differ in their price by $1.76, where the Xbox that has more bids is expected to sell for more. How does that sound to you right there? And I'll write it down. 2 Xboxes, that differ in their bid by 1 are expected to differ in their price by 1.769, I'll probably round that right there, dollars, where the Xbox that gets more bids is expected to sell for more. My head hurts. This one takes practice. This is what you need on your test verbatim right there. Let me copy it in the chat. 2 blanks that differ in their X by 1 unit are expected to differ in Y by B1 units, where the blank with the higher blank with a higher X is expected to have a blanker Y. This one takes practice, and it takes just thinking through. Now you might say, why can't we just do 201 interpretation? I always do a classic example of this. Let me just go right here to our classic survey 10 and explain to you why we do not use this interpretation right here. If you know the 201 interpretation, the 201 interpretation would say, do not listen if you want to not hear a bad interpretation. Or yeah. For each 1 unit increase in weight, or for each pound I gain, my height is expected to increase by 0.07 inches. So if I want to gain 7 inches, I could just do what according to this model? Like if I say, oh, for each pound I gain, my height is expected to increase by 0.07 inches. So if I wanted to gain 0.07 inches, if I wanted to gain 7 inches, I could just do what? I should go eat some cheeseburgers, right? But what should I do? So think about this as cause and effect, where you say, for each pound you gain, your weight is expected to increase by 0.07. Just gain some weight, right? But think about our interpretation. Our interpretation would say 2 individuals who differ in their weight by 1 pound are expected to differ in their height by 0.07 inches, where the individual who weighs more is expected to be taller. So let me say that again. 2 individuals who differ in their weight by 1 pound are expected to differ in their height by 0.07 inches, where the individual who weighs more is expected to be taller. These keywords like expected are very important, like expected. Don't say will. So this is the one where people get wrong, but be careful. Make sure to use 2 individuals who differ in their weight, that is the X variable, by 1 pound, are expected to differ in their, we did height for this one, where the person who is taller with the higher X, so these are people, that's your context, the person who is taller is expected to weigh, the person who weighs more is expected to be taller. And so this is why we do this interpretation here. It's very exact. It doesn't sound like cause and effect. It's very business analytics, where we're very precise with our words and very careful to not oversell what we're doing. So that is one where I see a lot of mistakes. Great job, Ella and Kayla right there. Another 100 points. Thank you both for being here. I love people following along. It's awesome work. The standard error of the slope. This is a weird one. The standard error of the slope. Oh, I just overwrote my X model, didn't I? No. Where did I save it last? I could have just scrolled up. There it is. Okay, the standard error of the X model. Kayla, anytime you ever tell your kids or something, like, or your parents ever tell you, for anyone that's not a parent here, like, we'll be there at 5. And then, like, when you get there at 5:05, and your kids are like, yeah, but you said we'd be here at 5, and you're like, I was just giving you a what? Use the words on the screen. When you say we'll get there at 5, and then you get there at 5:05, you'd say, that was just a blank. So if we say, I'll get there at 5, or yeah, let's do that at 5, and I show up at 4:58, and you're like, hey, wait, it's not 5, and you're like, oh, that was just a what? My when I said 5, I was just giving you an estimate. If you notice right here, it says estimate. I'm not telling you this value is true. I'm not saying that is the slope. That is not the intercept. This is my estimate of the slope. This is my estimate of the intercept. Any sort of estimate, and I know this is standard error, but don't think of the word standard error. Any sort of estimate, think of a U word, would have what? Because this is what the standard error is. It's variation. It's amount of spread of our data. I said maybe. That's what you say. I said maybe we'd be here at 5. That's what I say. It's my parents. Kidding. My parents are the ones showing up late all the time. It's not me. But so we'd have a certain amount of what in any estimate. If we give an estimate in statistics, we'd have a certain amount of what in that estimate. We'd have a certain amount of what in that estimate. If we said, here's my estimate, then I'd be like, this is my amount. I'm going to think of a U word. Like I'm like, around here, like I have a certain amount of what. So these standard errors, another word for standard error right here, is just our amount of what. I might be able to display it this way. Let me try to... I'm gonna try to make it look cool. Kind of. You're on the right track. I'm gonna show it. No, call names, right? There we go. Here is the better way to look at the output. You won't see it this way. But the standard error, so we could actually fix it up a little bit more. Oof. Went off the screen. The standard error is just your amount of what? And this is a great way to think about it. You have an estimate, and then all your estimates have a certain amount of uncertainty, right? So your estimate is just your amount of uncertainty. Does that make sense? And the t-value, which is the next thing to look at, we're going to interpret what that value is in a second, which is highly related to your assignment, is just the what of those two values. The t-value is just the what of those two values. The t-value is just the what of those two. Because just think, if you were to take this value right here, and you were to look at this, the t-value is just the what of those values. It's just your estimate divided by your uncertainty. That's all the t-value is. The t-value is just the estimate divided by the uncertainty, which is a ratio of the two. Sometimes it's called t-ratio in some output. But it's going to take what is your estimate and how much uncertainty do you have. Now just think about this logically. Do you want lots of uncertainty, yes or no? Do you want lots of uncertainty, relative to your estimate? Oh, no, great job, Kayla, right there. And I'll mark the rest of these parts. Do you want lots of uncertainty? Would you want lots of uncertainty in your estimate? Awesome, Kayla. Great work today. 100 points. Excellent work, Kayla. Would you want lots of uncertainty? No. You want your uncertainty to be relatively small. That's why we compare the two, the estimate compared to our amount of uncertainty. So we want this ratio to be rather large, which makes the p-value statistically significant. The larger the t-ratio in terms of absolute value, the more statistically significant it is. So if you look at your standard error right here, this is a relative measure of how uncertain we are in the estimate of the y variable, or the slope variable. So it would be blank. So blank is the amount, or standard error slope, whatever that is, which is this. Oh, no, it's this. Sorry, excuse me. Standard error slope is the amount of uncertainty I have in my estimate of the slope coefficient for my model. But the standard error of the slope refer to the intercept of the bids. The standard error of the slope is going to be this right here. That is the standard error of the slope. Sorry, I might have clicked on the wrong thing, James. That might be my fault right there, miscommunicating. Sometimes I do that. But the standard error of the slope is the one right there. Your output's going to look a little bit different. I'll show it in your output because I relabeled this for communication purposes. It's going to be this one right here. Did I mislabel? Oh, maybe I mishighlighted for a second. It's that one right there. That's the standard error of the slope. So the slope is the bids, because the bids is the x variable. And then this is the standard error of the slope, because slope is on the x variable. Does that make sense, James? So the x variable right here is this, or bids is the x variable, and the standard error, which is the measure of uncertainty, is this. So, yep, great work there, James. And so I would interpret this as this amount is the amount of uncertainty I have in my estimate of the slope coefficient 1.7690 for my model predicting price from bids. So you can add a little context right there. But we want to be able to communicate like that. That's how much uncertainty we have. Very important value for finding t-values and confidence intervals. And then we have another few, right? The r squared. So, we need to do the RMSE. Okay, the RMSE we just did standard error slope. The RMSE, which is this value right here, which also has standard error. Now, think about what standard error is. Standard error is uncertainty. So, residual uncertainty. Residuals are how much we miss by. So, we're saying, like, how much variation is there in the residuals? Now, you want this to be rather small. The residual standard error is actually going to be what is called the root mean squared error. Now, I want you to think about what root mean squared error looks like. Root mean squared error, which is residual standard error. Another name for it is this. Same thing as residual standard error. What two things in here cancel? And then it's an easy way to remember what it is. What two things in root mean squared error cancel out? And then we'll say, why do they cancel out? And we'll explain that. But what two things in root mean squared error cancel? If you were to think how two things in there cancel, like just mathematically, what two things would cancel in root mean squared error? Like if you think, oh, that just undoes the other. What two things cancel in root mean squared error? Root and square. So what are you left with? What is this called? And then we have to think, why don't we just do mean error? And the answer is because mean error would be 0, right? So we have to square it. So we square it to turn it positive. So this is just your average error. Like when you look at this model, what's my average miss? My typical miss? What's my typical error? Error is a miss, and average mean is average. So this is known as the typical miss of the model. Does that make sense, Ella, right there? If you cancel out the root and the square, you just get mean error, and it's also uncertainty in the residuals, residual standard error. So it's the standard error being uncertainty and residuals being uncertainty in the residuals, meaning variation in the residuals. So a few ways to understand it right there, but the typical miss my model makes is $60.36 when predicting price from bids. So that would be the typical miss my model makes in general format would be the typical miss my model makes is Y units when predicting Y from X. So it is in the units of Y. Be very careful. It's not always dollars. It's not percentages. But the typical miss my model makes is Y units when predicting Y from X. That's how much we're usually off by, like the typical size of a residual. R squared, one of my favorite ones. We talked about this earlier. R squared is going to be down here. Here's the R squared. So I always like to say R squared percent. How do I always lose percent? Of the variation in Y is explained by the variation in X. So right here we would say 10.36, it's in a percent. Remember, this is a decimal. We're going to turn it to a percent of the variation in price is explained by the variation in bids. Make sure to get your XY relationship correct right here, where bids is on the X and price is on the Y. So be very, very careful. The p-value of the regression right here is just going to tell us what? P-values just tell us statistical significance. So when we go down here to the p-value of the overall model tells us it is or is not, is/is not. Statistically significant. And let's put the p-value of, and then we'll put a blank, numbers thing. So p-value. The p-value of p-value. And so the p-value of, and this is actually 1, 2, 3. That's 4 right there. 5, 6. There we go. 6, 2. Oh my gosh. I thought wrong thing. And we can double check. Yep. Right p-value. The p-value of blank for the tells us it is statistically significant. So that right there has got it. I think that's got all the interpretations. Awesome stuff. And now we got to do a little bit of slope stuff. Let's look at that, and we're almost done. Okay, the slope of the regression line is on a sample, and it's just the slope, B sub 1, will be close to the truth. The slope of the regression line on the population obtain a 95% confidence interval for the slope for the regression model predicting price. All this good stuff right here. Use the confidence interval to determine whether the relationship is statistically significant. Okay, this is the end of the week stuff right here. So let's talk about confidence intervals here just briefly. And amazing work. That was a lot on interpretations. So confidence intervals for regression models. So when we build a confidence interval for the regression model, we need to think about how to build it first off. Now here's the code for a confidence interval for the regression model. Confint. There we go. But it's that easy, but what is it telling us? Ella, I want you to do the complicated mathematics of 10 times 2. What's 10 times 2? And I'll explain why I'm asking what 10 times 2 is. So the reason, and I'll show it over here visually, what is 10 times 2? And I'll explain conceptually. We estimated the intercept, which is the fun one to talk about for the moment. Ella, great work right there. We estimated the intercept to be something like 98. And then remember, we had uncertainty of about 10. Now, it's not exactly 10, but it was close to. If we go down 10, we've gone 1 standard error. Go down 10 again, we've gone down 2. We go up 10 here, we've gone up 1 standard error. We go up 10 again, we go up 2 standard errors. So I want you to look at this right here. With this, I have covered what percent of this curve? So what percent, back to stat tool 1, right here, what percent of this curve have I covered? By going down, and this is a curve with a mean of 98 and a standard deviation of 10. So what have I covered? Oh, you're fine, Ella. No worries. Great work. I'll start explaining. Ella, amazing work. Thank you so much, Ella, and good practice today. So I've covered 95% via stat tool 1. And think about this. The standard error is our uncertainty, and then the estimate is the center of our interval. So when you look at the code right here, with what we had in the output, let's go ahead and look at the output again. We had an estimate of 98 with an uncertainty of a little less than 10. And then if you look at our confidence intervals, that's what's building it. Same thing for the slope right here. If you were to go here to this and add to it basically 2 uncertainties. So let's go here, add to it 2 uncertainties. There's the upper bound, or very close to. And here's the lower bound, and those will be close to it. There's the lower bound, and there's the upper bound. Now, it's not exact because it's not exactly 2. It might be closer to 1.96 for a lot of data, and that's the classic z-score for a 95% confidence interval, but we're using t, which is a more fine calculation. Technically, 1.95996 to be exact. And but it's probably not going to be quite that because, once again, we do not have, you notice they're a lot closer now. Yeah, they're a lot closer. But it's 1.96. But if we're going to go exact, it's going to be 1.95. Or we could do this. I'm just having some fun here at the end. Let's go to p-norm. I always get p-norm and q-norm confused. Never get them both correct. P-norm, and we want the quantile. Let me double check right here. Cool. Okay, that's the percent area below the curve. We want q-norm. There it is. Yep, and there it is. I don't know the next digit, but it's 1.95996. Most people, of course, are normal and just say 1.96. But it is 1.95996. One time I got in trouble, not in trouble in class, but the teacher was like, it's 1.96. And I was like, 1.95996. And they're like, no, it's not. And I was like, but the extra digits. And they're just like, why would you? I'm like, why not carry more digits? Why not go right here and go to options? I'm slowly losing my mind. There we go. That's what it actually is. There's the actual z-score for a 95% confidence interval. Problem is, and I want to make this clear again, we're not actually doing z-scores. We actually are doing t, and I believe we have something like how many degrees of freedom? 147 intercept slope. I think 147 degrees of freedom. Close enough. And so there's the t. We could confirm by going back to our equations and seeing if it works. This is why we don't do this stuff by hand. There's that. And here's the minus on it. And then the confirmation that we have the right answers. If we are doing it correctly, these should be nearly identical. 2.617, and there it is right there. And we are down to decimal place accuracy now. So however we're doing, we're very close to the right answer. But here's the point. We don't do this kind of stuff. Don't got time for this here. We need to understand what these intervals are and what they're telling us. That's very important. So let me fix my options so I don't get the crazy digits. We're going to go to digit 7 as we usually do, and we need to know this output right here and what it means. I'm telling you with this output what I think the slope might be. I think the slope is possibly between the values of 0.9 and 2.6. I'm saying to you it might be about this, or it might be this. Maybe more like this, but this is still positive. And I'm saying maybe the slope is 0.9, or maybe the slope goes as high as 2.6. That's what we're communicating to someone. Like, I don't know, with 95% confidence, the slope is probably somewhere between 0.9 and 2.6. That's how we'd interpret it as normal people. We can show them all the mathematics and the t stuff and all that great things, talk about the difference from the t to the z, but we're really just trying to sell, or tell people, I think the slope is probably somewhere between these values. Now, why does this matter? Because we can tell if our model is statistically significant. The slope is the xy relationship found in the x variable. The whole point of this is to know, is the slope 0? If the slope is 0, there's no relationship. Because remember, going back a bit, that would be the naive model. The naive model has no relationship. It's a flat line. There's no x variable. So when you think about this, if we have a slope here of 0, it's not statistically significant. Now, do remember, we already looked at the output, and we know that our model is statistically significant. So this idea right here coincides with the model output, where the model is, graphics output, you're so fun. This output coincides with the model that has a statistically significant p-value for the model, and also the slope does not contain 0. So I think the question itself asked, well, how would we interpret this? So it says, right here, code creating the 95% confidence interval, we got that. So you could literally run this code right here. It uses the extra argument. We don't need to change the level. You can change it to whatever you want, like 99, but it wants a 95. It's still significant at the 0.01 alpha level. 1 minus your confidence interval is your alpha level. And we do see that we have good evidence that there is a relationship between the x and the y variable, because 0 is not contained as a possible value for the coefficient of the slope. The slope is probably not 0. We're doing better than the naive model. We wouldn't believe that the naive model and this were identical unless 0 was contained in the interval estimating the slope. And that's a big takeaway right there. If 0 is contained in the interval estimating the slope, not the intercept, if the interval contains 0 where we estimate the slope, then we'd say, maybe it's just the naive model. Maybe the naive model and it are very similar, because naive model's got a slope of 0, but our model does not have a slope of 0, or at least we have good evidence of that, and thus our model is statistically significant. With that, it's time to end. If you have questions, email me, Puppet Shark. Time to go. Awesome work, Puppet Shark. Hacker Man out. Bye for now, everybody. Bye. Make some dinner. It's not time for class. Time to go.